Come on in, everybody. Sorry about the delay. Come on in. Come on, everybody. Come on, everybody. Got more people coming in. Anybody have any questions while we're waiting for everybody to come in? Ask questions about course material, tests, all that good stuff. I do have your test one made, by the way. It should be posted right after class. At least by tomorrow morning, if not immediately after class. But anybody have any questions about anything else?
Are you going to repost the syllabus?
Yes. In fact, you know what? Yeah, I don't think I put the final version up. Yeah, I need to do that for you. Yeah, thank you for reminding me of that. I completely forgot. I remember I took it down to fix it because I had some really bad erroneous dates, and then I just never put the updated version. So yeah, I'll do that. I apologize. Was there something specific you needed to know about it? Something that you're looking for?
Well, I just wanted to keep track of dates and I wanted to see like the email format for you because I wasn't able to take a look at it.
Gotcha. As far as sending me email, the main thing is I said make sure you send it from your TCC account to make sure the subject line begins with PHY 242 night. That would be fine. You could also do NO1B, but the main thing is I need T42 and the fact that it's either a night class or an online class because I have two 242s. And make sure you include your first and last name. But other than that should be all. I've been paying attention and trying to catch the ones that haven't been sent to me properly. But I have missed a few because that's normally the way I do the search is I do a search for PHY 242 night. So anything else, anyone? All right. Well, when we were last working, we were actually working on calorimetry. And in fact, I was just looking at the last problem we worked, which I think I didn't even get started. Oh, maybe. Oh, I might have. I think I might write the solution after class, and y'all can see it in the notes. But I'll start with that. It was how much heat is required to raise the temperature of a 20 kilogram aluminum cooler from 10 degrees Celsius to 80 degrees Celsius. And then part B, what if it is filled with 20 kilograms of water at 10 degrees Celsius? Okay. So I thought I'd start with that. And that's sort of the most important thing from this chapter. When I'm looking at chapter 19, for instance, the topics are heat as energy transfer, internal energy, specific heat, calorimetry, bomb calorimeter, latent heat, evaporation. It's a very uncommon word for me, evidently. Kinetic theory of latent heats, the first law of thermodynamics. So really the major things here are one, calorimetry. Can we solve problems where you're assuming something, some system is isolated from the universe, like with a cooler or something like that, and heat can only be transferred from one part of the system to the other part. So like the example that we often do is the same one we do in class, whereas you take a hunk of metal and you put it in a bottle of water, you start boiling the water, and as long as the metal's been submerged in there, it's a conductor, it should come to equilibrium with the boiling water pretty quickly. But once it starts boiling, you leave it in there for 3 or 4 minutes or whatever, just to make sure it's at equilibrium. And then you pull it off. Hopefully it's pretty dry, and you immediately dip it in a measured quantity of water in a measured aluminum cup. In other words, aluminum cup whose mass you know. And then that cup will sit inside of a sort of like a cooler situation called a calorimeter, where it basically isolates it from convection and conduction, but not radiation. And the heat losses are pretty small that way. So what ends up happening is when you put the metal in, it heats the water up, and then they come to equilibrium when the water, the metal that you put in it and the aluminum cup are all at the same temperature, the temperature will stop climbing, stop climbing, stop climbing. And then right as they reach equilibrium, it'll reach its highest temperature and then start to fall back down, because at that point, the water and the metal and the aluminum cup are all at a higher temperature than room temperature, and the room will start to receive heat from that object. So the temperature will start to drop. So if you look for that peak of what the highest temperature it reached was, you can use that to determine, for instance, what the specific heat of that metal was. Or if you knew the metal, you could use it to determine what the specific heat of water was. Or if you knew water and specific heat of that particular metal, then you could use it to determine the specific heat of the aluminum cup. So that's sort of the typical scenario with calorimetry. The other thing with calorimetry, though, is, and that's what I'm going to start on tonight, is there's these things called heat diffusion. And we started off in this course talking specifically about the molecular theory of matter. You know, matter is made up of atoms and molecules. And of course, molecules being the smallest part that still has the behavior of the compound, and an atom being the smallest part that still has the properties of the element. So, and of course, you can't go any higher than that. Once you get higher than that, you're just basically getting mixtures. And mixtures are sort of like a salad. You know, if you grab 3 bowls, you might not get a single tomato in it, even though there was plenty of tomatoes in there. Whereas an actual compound, if you chose an appreciable amount, you definitely get atoms in there. So anyway, so that's what we're going to work on. Anybody have any questions about anything that we did last time? So the test is going to be, you guys meet on Tuesdays and Thursdays. So the test will come available sometime tonight or first thing in the morning. And like I said, I got it made. I just got to set up the settings. And you'll have until Monday at 11:59 p.m. to take up to 3 attempts. So I'm going to give you up to 3 attempts. Remember my online test, I've taken down the net because I know that a lot of times good students obey the rules and they get sort of hamstrung by the difficulty of the test, whereas students that are a little less moral might actually deviate and go look in their book or look on the internet or something like that. So I've gotten rid of that by allowing you guys to search the web, search your textbook, search your notes, look at any textbook, look at any notes, and even do Google searches. Okay. The main thing I'm trying to not let you do, and this is what's considered cheating, is get any assistance from anyone that has already seen the test. So once the test becomes available, which is today, basically anything that's been put on the internet since today or later is something you shouldn't be looking at, specifically because that would allow, you know, one of your fellow students to go look at the test and then make a really helpful help sheet on it and stick it on the internet. And that would be sort of circumventing the rule. But in fact, it's not circumventing the rule, because if you communicate any methods with someone that's already taken the test about anything on the test, then that's cheating. So just don't do that, and you're golden. And generally, the test averages for the online tests are quite high. Usually, mid to lower 90s is not an uncommon average. But again, that's I have no idea who's taken that. I know you've got access to the books. It's really supposed to be a learning experience and a sort of a capstone to making sure you've learned what's relevant. So any questions on that? All right, well, let me start off first. I'm going to turn this on and make sure, because I can't remember exactly everything that happened, I'm going to go ahead and make sure you follow what we did on the very last one. So what I'm going to do is do share screen, and I'm going to share it with my iPad. And then I'm going to tell my iPad to share screen with William's iMac. Oh crap! It's a new week, so it makes me download something again. I'm hoping that's like something that Zoom does for security. Otherwise, it's just a dumb thing, and that makes me angry. Okay, it's loading up now. I'm also going to try to see the chat in case anyone follows up on there. Thanks, Angelica. I see your comment. Okay, so this was the question. I said, how much heat was required to raise the temperature of 20 kilograms of aluminum cooler from 10 degrees Celsius to 80 degrees Celsius? And then what if it's filled with 20 kilograms of water? So in the first case, really the only thing that's changed in temperature is 20 kilograms of aluminum. You can look up in the table, it's called table 19-1, which is at the very beginning of section 19.3. They have a table of specific heat. They've got it in joules per kilogram, but they also have it in kilocalories per kilogram. We normally use it, or I in chemistry normally uses it in calories per gram. So that's what I did here. But yes, the specific heat for aluminum is 0.22. And then all you got to do is figure out, okay, I'm actually trying to raise the temperature. And the formula for changing of a temperature is that the heat required to change the temperature of a mass M is directly proportional to M. That's thumbs up, thumbs up. It's directly proportional to the change in temperature, meaning if you go from 90 to 91, that might take a certain amount of heat. But if you go from 90 to 100, then that might take 10 times as much because they're thumbs up too. In other words, the delta T, the change in, which means final minus initial, that difference in temperature is proportional to the heat added. And then finally, what we use for a constant is not only a constant, but something that takes into account the properties of the material. And that's what we call the specific heat. And the word specific means it's per gram or per kilogram, or there's also versions where you'll say per mole. So anytime you go and do something and it has the word specific, you should realize that that specific means it's per gram, per mole, or something like that. Okay. There's even a, what is it? What do they call that? I think it's like specific density or something like that. So there's quantities like that, but you'll run into them when you take thermodynamics for engineering if you have to take that. So what we have here is MC delta T. Of course, I've got the mass in kilograms, so we can think of converting that to grams, or by that 1,000 grams per kilogram, or we can think of that 1,000 grams per kilogram as canceling the grams in the specific heat and turning everything into kilograms. Either way, it doesn't matter. It's the same factor and it only happens once. And you see that it's about 3.08 times 10 to the 5th calories to raise a 20 kilogram, essentially a 20 kilogram block of aluminum. It would be the same whether it's a block of aluminum or a hollowed out aluminum cooler or a hollow aluminum sphere or a solid small aluminum sphere. All those really don't matter. Where that stuff comes into play is in terms of conduction, which we'll learn about later as well. But in conduction, what we learn is that the heat that's transferred from one thing to another is takes a certain amount of time, and the amount of heat delivered per unit time is directly proportional to the difference in temperatures between the hot thing and the cold thing. But it's also directly proportional to the surface area or the cross-sectional area of the contact spot, and it's inversely proportional to the length apart they are. So that we're going to learn as well in chapter 19. But like I said, the main things that are most important for chapter 19 is these calorimetry calculations, the first law of thermodynamics. And then you'll see we get into isothermal processes, isobaric, isochloric, isovolumetric, adiabatic, all those different things. And we cover that in light of our knowledge of these first law of thermodynamics. And then finally, we talk about how is energy transferred from, or how is heat specifically transferred from one object to another. And there's 3 ways heat can be transferred. It's conduction, where the 2 things are touching, and then heat flows from the hot object to the cold. There's convection, and the way we normally picture this is you could imagine, for instance, a hot metal stake or rod or something being at the bottom of a swimming pool, and then what happens is the water gets around the hot metal stake. That hot metal stake warms up the water. The water, becoming warm, actually gets less dense and floats up to the top, and then can deliver some of that heat to something above. So that's sort of one way of thinking about convection. That's why, for instance, 7-Eleven now sells you pizza and hamburgers and stuff like that, and they can cook it really quick because they're using convection ovens, or you probably think of them as air fryers. and air fryer is essentially a convection oven. It allows not only the introduction of heat, but it allows a medium, in the case of the air fryer, air, to actually distribute that heat more quickly, more rapidly. So you get the regular radiation effect. You also get a little bit of conduction from where it's sitting on the pan or the rack or whatever, and you get convection. So that's why things can cook a little quicker. Now for part B, what we were doing was saying, okay, well, what if I add water to it and it's 20 kilograms of water? Well, 20 kilograms of water all by itself takes 1.4 times 10 to the 6 calories. So that's essentially about 50 times more energy than the aluminum cooler takes all by itself. So 1.4 times 10 to the 6 calories versus 3.08 times 10 to the 5th calories. But what you have to do to actually take the cooler and the water in it and heat that all up to 80 degrees Celsius is you've got to take that amount of heat, 3.08 times 10 to the 5th calories, that's got to be added, and the 1.40 times 10 to the 6 calories has to be added, so that the total is the sum of the two. Any questions on that problem? So I just wanted to put that on there so y'all would understand what I was saying. So now we have to add this quantity and this quantity, and that's what's going to be the total amount of heat required to do that. Now, I haven't named this yet. This is obviously not the correct name that this file is going to be. Oh, yeah, that's right. Y'all can't even see the name that the file is, but the name of the file will be PHY242N01B 09052023. So that's what the file name will be when you go to Google Docs if you need this. So we were doing calorimetry type experiments or calculations, and we did the cooler idea. Now what I wanted to do is, there's a nice conceptual example in 19.3. It says you accidentally make a bad mistake by letting an empty frying pan get very hot on the stove. In other words, 200 degrees Celsius or even more, okay? What happens when you dunk it into a few inches of cool water in the bottom of the sink? So you've realized you've screwed up, you've put your cast iron frying pan, for instance, on a fire, and it got out of hand and it got way too hot. You couldn't pick it up. You had to use towels, also that sort of stuff. And you quickly think, well, I need to be able to lay this down somewhere, so I better quickly cool it off. So your idea is to put it in a vat of water, specifically a sink full of cool water. And it says, what happens when you dunk it into a few inches of cool water in the bottom of the sink? Will the final temperature be midway between the initial temperatures of the water in the pan? Will the water start boiling? Or, and here's a key point, or what, but they're saying assume the mass of the water is roughly the same as the mass of the frying pan. Anybody want to take a guess at what they think that answer would be? Is it going to be halfway between the temperature of the frying pan and the temperature of the water, given that they're about the same mass, the water and the frying pan? Is it going to be a lot closer to the initial temperature of the water, or is it going to be a lot closer to the initial temperature of the frying pan? Nothing. Okay. Well, and this is not unlike, in fact, when you do that specific heat lab, which I think you guys will be doing if you haven't already did it. Most teachers do it in the 242 class. Some of them do it in the 241 class. So depending on who your lab instructor is, they might do it. But the main thing is they ask that same question. Hey, you're going to take about 50 grams of water at, room temperature, which is about 20 degrees Celsius. And you're going to put, something like 20, 30 grams of a really hot metal, 100 degrees Celsius, in the water. What do you think the final equilibrium temperature would be? And it'll have answers like, it started at 20, so it'll be like 22, or it'll be like 98, or it'll be like halfway between the two, which is 120, 100 from 20 is 80. So you go up 40, that'd be 60 degrees Celsius. So those are three answers. The answer is specifically because metals, as you see in that table, have very low specific heats, like copper is like 0.09 in calories per gram degree Celsius, or Celsius degree. But water is a high specific heat thing, and that high specific heat thing has a specific heat of 1.00. So 1.00 is way bigger than 0.09. And then the other metals like aluminum's 0.22. I think steel is 0.11, something like that. So yeah, when you put the actual cast iron frying pan in a roughly similar weight of water, but the water's, cool, the water's not going to change temperature very much. So if the temperature was say 10 of the water, and then you put the 200-degree frying pan in there, it wouldn't be unreasonable to expect it to only raise to maybe 12 or 13. Okay, any questions on that? So that specific heat is thumbs up with the heat as well. So the larger the specific heat, the larger the amount of energy it takes to change the object's temperature or the substance's temperature. So let's look at another type of problem. Let's imagine, for instance, a 250 cc glass, or excuse me, a 250 cc glass of tea. God dang it. Let's say quantity. That's what I'll do. Quantity of 95.0 degrees Celsius is poured into a, dang it, I keep turning into an eraser, into a 200-gram glass, and there I go right in lowercase again, glass at 25.0 degrees Celsius. What will be the common final temperature? And common means glass and tea. Now, in this case, and there's good arguments against it, by the way, but in this case, we're going on the assumption that tea is essentially water. And in some sense, it is like, you dip a tea bag in water, very small mass is transferred from the tea bag into the water. So in that sense, there's not a whole lot of tea in it. And therefore, we're going to argue that the specific heat of tea should be the same as the specific heat of water. If you're talking about hot tea, that's a little safer bet. But if you talk about sweet tea, for instance, that can be quite a bit different because sugar can be absorbed a lot. The tea is definitely going to be, somewhat contributory to the weight as well, even if it's a small amount. So there's been instances, for instance, where you can determine a huge difference between even the density of the liquid that is sweet tea compared to the density of water. So that might not be a safe a bet with cold tea, but maybe in warm tea it is. Now, if you're just putting milk in it or cream in it or something like that, like some people do, then all bets are off. But let's start with our solution. So here's our solution. What I do with calorimetry experiments or calculations is I take and I add up all the things that are losing heat. I add up all their heats, and I set that equal to all the things that are gaining heat. Okay. Now, the problem with that is most people, like your textbook and a lot of different textbooks, a lot of them use delta Q is equal to 0. And basically what that is the losing heat things, their temperature is going to go down. So the delta T part of Q equals MC delta T is actually negative. and then the delta T part of the things that are gaining heat, they're actually going to warm up. So that Q is going to be positive. And basically what they would do to convert this to that type of problem is you take Q gaining heat minus Q losing heat equals 0. That works fine. That's the exact equivalent to delta Q equals 0. But what I find is when we start talking about heats of fusion, heats of vaporization, what we call latent heats, it gets really kind of confusing in the stress of a test situation. And you often make a mistake as to whether the heat of fusion should be negative or positive. So by doing it this way, I just make sure everything is positive, and then it all works out. So that means our classic definition, the delta T, the big, triangle T, I've told y'all 1,000 times, probably. Well, maybe not 1,000 because I've only had you for a couple of weeks. But if you had me for 241, you would have had probably another 900. But the main thing is delta almost always means final minus initial. So if you see a delta Q or a delta T or a delta E or anything like that, what they really mean is final value, whatever symbol comes after the delta, minus the initial value of that same symbol. Okay. In this version that I'm doing, where Q losing equals Q gaining, everything's going to be positive. So we have to flip the orders. So it's not always final minus initial, but that's the only real caveat for this. Now, what we do need is we need the specific heat of water. So this one, I'm just going to say not me. Okay. But I do need the specific heat of water. And I like the calorie figure because that's a really nice number. It's 1.00 calories per gram Celsius degree. Notice how the degree comes after the Celsius. That means it's meant to be multiplied by a difference in temperatures. And the difference in temperatures, we just use as sort of a bookkeeping device. We put the degree after it if it came from a subtraction, whereas we put the degree before the C or before the F if it's just a temperature. Now, we also need the specific heat. The water was essentially the same thing as the specific heat of T, as I told you, but we also need the specific heat of glass. So I'm going to look back on that table, and that I said was at the top of section 19.3, and I'm going to look for glass, and I see glass has a specific heat of 0.20 calories per gram Celsius degree. Okay. Sorry, I'm writing this so small. I will try to do better. So calories per gram Celsius degree. And of course, that word over here is T. I didn't think that came out very clearly when we're looking at it, at least at the size that it was. So I'm going to say T and water are approximately equal. Okay. So what we're talking about here is pouring really hot tea into a somewhat cold glass. It's actually not cold. 25 degrees Celsius is pretty warm, but it's cold relatively. So it's colder than the tea is. And the main thing is, though, and this is also an equivalent version of the second law of thermodynamics, heat flows from the temperature or the body with the high temperature to the body with the cold temperature, period. You can make it do otherwise, but that's going to cost energy, and that's another version of the second law of thermodynamics. But generally speaking, heat spontaneously flows from a hot body to a cold body. So with that in mind, the thing losing heat is really just the tea, and the thing gaining heat is really just the glass. So I'm going to say the losing heat is going to be the mass of the tea. Now, I told you that it's a 250 cc quantity of tea. Well, does anybody recall what the density of water is? That was very good, by the way, Taylor. I didn't see that until now, but good job. Does anybody know what the density is? So this is one of those really fun numbers. It's nice. It's like 1 in a lot of different things. So for instance, the density of water, which again, I'm arguing is approximately the density of T, but the density of water can be written as 1 gram per cubic centimeter. Well, actually, the way I wrote it, I wrote cc, so I really shouldn't write cc and then cube it like a dummy. We're going to say, whoa. We're going to say the density of water is equal to 1.00 calories per gram Celsius degree. Dang it, why did I write specific heat instead of the density? 1 gram, there I go again. 1 gram per centimeter cubed, which is the same thing as a cc. So I can say 1.00 grams per cc. That works. It also happens to be, and this is just for your edification, it also happens to be 1.00 kilograms per liter. It also happens to be 1.00 grams per milliliter, and it also happens to be 1,000 kilograms per cubic meter. So those are a lot of different things. And I offered my students, you included, as an extra credit, convert the density of water to ounces per fluid ounce. Okay, so that's a neat little exercise to try, and it'll give you another interesting point. So let's do heat loss equals heat gained. I'm using the density of T being approximately the density of water. So 250 cc's of T is essentially 250 grams. So using the formula of Q equals MC delta T gives me 250. I'm going to put a decimal point on that just to let you know that I'm treating that as if it's 3 sig figs. So that's 250 grams times the specific heat of T, which is water. So I'm going to say 1.00 grams. Dang it, there I go again. Now all of a sudden I can write density. Calories per gram Celsius degree. And in fact, the T is going to get colder, right? The T is coming in at 95 and it's going to reach a lower temperature. So if I did T final minus T initial, that would be a negative. I don't want that. So what I'm going to do is I'm going to say 95.0 degrees Celsius minus T final. Okay, that way this quantity right here is definitely going to be positive. So that's my losing heat side. My gaining heat side is the glass, and the glass is 200 grams. So I'll say 200, put a decimal place there as well. And then the specific heat is 0.20 calories per gram Celsius degree. Now this thing's heating up. So you can actually have the final temperature be first. So that'd be T final minus 25.0 degrees Celsius. Okay. So I can multiply 250 times 1 and then times 95. Well, if I had 250 times 1, it'd be 25,000 if the 95 was 100, but the 95 is not. So I actually have to take away 5 of the 250s. So I can do it that way, or looks like I might have to do it that way because I've seemed to have moved my calculator to a different place. I'm going to pull up this calculator and hope for the best. Y'all should definitely calculate this with me to see if you get the same thing. So I'm saying 250 times 1 times 95. And that gives me 23,750. So that's 23,750. Notice by multiplying grams times calorie per gram Celsius degree times a degree Celsius, I essentially get calories. Okay, it's actually a little bit off because technically I haven't done a subtraction with that 95 yet because the variable's in there, but that's not a big deal. Now I have to do that same thing now, the 250 grams times 1 times -1, because there's a coefficient of -1 in front of the TF. So I'm going to say minus 250 point, and that's going to be calories per Celsius degree times T final. Now over here on the right hand side, I got 200 grams times 0.2. that would be 40. So I've got 40.0 calories per Celsius degree times T final. And then I have to take 200 times 0.2, which would be 40, and then 40 times 25 would be 100, and then 100 times 10 are 1,000. So that'd be minus 1000. I will say that's one extra sig fig, and that should come out in exactly calories. So let me check with my calculator to make sure that that math I did was correct. And actually, let me make this calorie a little bigger because I want y'all to be able to read. That's helpful, Cosmo. Thank you, buddy. No more. All right. So what I said was 200 times 0.2 times 25. And I said that was 1,000, and that is correct. Okay. So now what I've got is two terms with TF in it, one on each side of the equation. If I pull the one on the left to the right-hand side, it'll go from being negative to positive. So I end up getting 290.0, which actually has one extra sig fig, and that'd be calories per Celsius degree T final. And now I can pull this 1,000 from the right-hand side to the left-hand side. That'll become a positive. So now I have 24,750 calories on this side. Of course, the 5 and the 0 were not sig figs anyways, because I had multiplied it with only 3 sig figs. So now I've got 24,750. To solve that for T final, I have to divide by 290. So 24,750. I'm going to say divided by 290. And that's going to give me T final on the right and 85.34 degrees Celsius. So the final temperature T final is supposed to be about 85.3 degrees Celsius. Notice that that is in fact quite a lot closer to the initial temperature of the tea than it is to the initial temperature of the glass. So that's just like that other problem where we were throwing a hot metal pan in water. Anybody have any questions on that? Oh, I was just looking at the 5th edition. They did a problem just like this, but in one case they did it with heat lost equals heat gained, which is the way I did it. And then they redid that same example with what they called an alternate solution. And in that case, they said delta Q equals 0. So they actually show you both ways. Whichever one you want to do is up to you. I've just always found the thing losing heat, if you add up all those heats and then take all the heats for the things that are gaining heat, put that on the other side, that's always worked nicer for me because I don't make that careless mistake when it comes to heat of fusion, heat of vaporization, heat of sublimation, that kind of thing. Any questions on that? All right, well, let me show you another problem really quickly. So let's say I'm actually looking at an example in your book. It says an engineer wishes to determine the specific heat of a new material, a new metal alloy, actually. And it says that a 150 or 0.150 kilogram sample of the alloy is heated to 540 degrees Celsius. It is then quickly placed in 0.400 kilograms of water at 10 degrees Celsius, which is contained in a 0.200 kilogram calorimeter cup. The final temperature of the system is 30.5 degrees Celsius. Calculate specific heat. So this is exactly the lab that I was talking about. So, and you can look, figure 19.4, I'll say that. See figure 19 or excuse me, they said a dash, so 19-4. Basically, that shows a calorimeter, sort of like the one we use in class, where in class we actually have this little cardboard wafer that holds the lip of the small aluminum cup, because it's slightly smaller than the lip flares out on the aluminum cup. And then it sits inside of the bigger aluminum cup that comes down like this and then goes in some and then goes back down. It sits on that little ledge. So the only conduction that could possibly take place has to go through that thin little face that actually has a thickness of on the order of maybe 2 millimeters and a width, because it's technically rectangular, a width equal to the circumference of that small part of the cup. So that circumference times that 2 millimeters is the critically small area that it can use for conduction. So you've really eliminated the vast majority of conduction. Plus, cardboard or the other things they make that out of are very non-conductive materials, so they're better as insulators. And by having it spaced out where it's not touching the outer walls of the little inner cup to the inner walls of the bigger aluminum cup, then conduction can't happen that way. And in fact, it also stops convection because it's got a little cap over it. And yeah, there's an air cavity between the big cup and the little cup, but that air can't circulate. So convection is not an issue either. So that's what happens. I'm going to go ahead and write down the information from the problem. So what we know is the mass of the alloy. The mass of the alloy, which I'm going to call N sub A, is 0.150 kilograms. The initial temperature is in fact 540. I don't know why I wrote that backwards, but I decided to write the 4 before I did the 5. 540 degrees Celsius. I'm treating that. I put that decimal down there so I can treat it like it's 3 sig figs. And the mass of the water, which I'll call W, is equal to 0.400 kilograms. And the mass, oh crap, the alloy does not work very good. Let's say, I'll say metal. So the mass of the metal instead of the alloy. So I'm going to erase this little subscript A, because guess what? Alloy and aluminum both start with the letter A, and I didn't see that coming. Yeah, it's not one of my better days. All right, so now the mass of the aluminum, which I'll put the chemical symbol to, that helps us a little bit. That is in fact 0.200 kilograms. And I should call that the initial temperature of the alloy, which again, I should change that A there as well. So let me do that. I'm going to say the initial temperature of the metal is that. And I am going to say the initial temperature of the water. And that's actually the water and the aluminum. That initial temperature is in fact going to be 10 degrees Celsius. And what they told us was T final is actually equal to 30.5 degrees Celsius. Now they only give one temperature for the final. Does everybody understand that? Why they didn't give us, a temperature for the final for the aluminum, a temperature for the final for the water, and a temperature for the final for the new metal alloy that they're investigating. Anybody know why? So I'm trying to get you to literally imagine the experiment. So essentially what they did was they used some mechanism and some device that can measure the temperature of a metal. And the mechanism they used was something that allowed the metal to get up to 540 degrees Celsius. Okay. And then they use this device. Maybe it's an infrared camera. I don't know, but you can use some device to then determine the temperature. And if the surface, for instance, stayed that temperature for a long enough time, and that's what infrared cameras do, is they measure a surface temperature. So if that stayed that way long enough for a very long time, then because the metal is a metal, it's a pretty good conductor of heat and electricity. So the heat will actually have flowed from the surface to the inner parts, and all the things should be completely at 540 degrees Celsius before they stick it in the water. Now they stick it into the water, which is at 10 degrees Celsius and is also at equilibrium with the aluminum cup, which is at 10 degrees Celsius. And you just watch the temperature gauge until it reaches a max and then starts to go back down, because once it reaches that max, that means the water, the aluminum cup, and the metal are all at the same temperature. That's why there's only one final temperature, 30.5. Okay. Hopefully that makes sense. If your teacher's doing what I do with my lab students, if I see that they're not contributing, like if you've got one person in one group and maybe another person in another group that just aren't contributing to their personal lab groups, then I say, okay, well, we're now, because y'all are in trouble for doing this and I'd already gotten on you, I make y'all have a comprehensive lab final. And these are the types of questions they'd ask. So I'm trying to make sure you are ready for such things. And the way you would be is by understanding the experiment. All right, so I'm going to use my same old process. Here's the solution. What I'm going to use is Q losing is equal to Q gaining. You'll notice I put all sorts of words on there. Sometimes I'll say Q hot and Q cold. That works too. Okay. But the main thing is you just have to have everything that's losing heat on one side, everything that's gaining heat on the other side, and everything positive. So if we do that, we also have to use Q is equal to MC delta T. So the thing that's losing heat is just the metal. So what we have is 0.150 kilograms times the specific heat of the metal, which is what we're asked for. They said calculate the specific heat. So I should probably write that up here. C metal equals question mark. And then the change in temperature, of course, is going to be big minus small, so I can make sure it's positive. Well, the big change in temperature for the metal alloy is really the bigger of the two temperatures is the initial temperature. So I'm going to do initial minus final. So that's going to be 540 degrees Celsius minus 30.5 degrees Celsius. So that's all the things that are losing heat. Now gaining heat is the water and the inner aluminum cup, not the outer one, just the inner one. So the water, as we said, was 0.400 kilograms times I'm going to use the calories per gram, or excuse me, the joules per kilogram, since I have all the masses in kilograms already. And of course, you know from the conversion factor that 1 calorie is the same thing as 4.186 joules. So that's what we're going to use. So in terms of joules, 4,186 joules is what's required to change 1 kilogram of water 1 Celsius degree. So you can really, it's a lot easier to see the difference here when you see 4,186 as opposed to just idio-bidio 1, right? I said idio-bidio. That's pretty cool. All right. Now, in this case, the water is actually going to end up with a higher temperature than the initial temperature. So you're going to do final minus initial. So that'd be 30.5 degrees Celsius minus 10.0 degrees Celsius. And that's the water term, but there's also an aluminum term. So that is in fact going to be the mass of the aluminum is 0.200 kilograms. The specific heat of aluminum, at least in these units, is 900. And that's joules per kilogram Celsius degree. And again, that's going to be raising its temperature. So that's 30.5 degrees Celsius minus 10.0 degrees Celsius. Okay. So we can work out the left-hand side by multiplying 0.150 times 540. So 0.150 550 times 540. That is just the kilograms multiplied by the Celsius degrees. So on the left-hand side, I'm going to get 81 because that's what the multiplication gave me. So I'm going to say 81.0 because it had to be 3 sig figs. And I'll put another 0 there just to make sure it's an extra sig fig. And that unit comes out in kilograms degrees Celsius. And all of that will be times cm. Now the other one is going to be 0.150. Actually, I don't have to do it that way. Let's go ahead and do the subtraction. I forgot I had both temperatures. So I'm going to erase that and do 0.150. Let's see again. Actually, I'm going to do 540 minus the final temperature, which is 30.5. So I'm going to say minus 30.5. And that is 509.5. Now I'm going to multiply that by 0.150. So 509.5 times 0.150 is equal to 76.425. That's 2 extra sig figs. And really what that is kilograms times Celsius degrees. So notice that came from a subtraction. So it is actually correct to write Celsius degrees. And then all that's going to be multiplied by the specific heat of the metal alloy that they're investigating. Now, the water term, I really want you to see the difference of the water term versus the aluminum term. So I'm going to do them separately. First off, I have 30.5 minus 10. Obviously, 30.5 minus 10 is 20.5. That's 20.5. And now I'm going to multiply that by 4186. And now I'm going to multiply that by 0.4. And that's going to give me 34,325. And notice that unit comes out in joules. Okay. Not only that, it's only the 3 sig figs. So that 2 5s is 2 extra sig figs. There's actually a 2 after it, and then that's the total number. But we're good right there. Now I'm going to do the same thing for the aluminum. So I'm going to take 20.5. $20.5. I'm going to take that and multiply it by 900. And now I'm going to take that and multiply it by 0.2, which is the mass. And that gives me 3,690. That's 1 extra sig fig, and that's joules. So I'm going to take that 3,690 and I'm going to add the 34,325. And that should give me a little bit over 37,000. In fact, it gives me 38,015 joules on the right-hand side with 2 extra sig figs. And that's equal to 76.425 with 2 extra sig figs, kilograms Celsius degree times cm. So that tells me cm is going to be that 38,015 divided by 76.425. And that gives me 497.4. Notice the units are joules per kilogram times Celsius degrees. I want to double check my math on that. Did anybody else do that calculation? Okay, I'm just going to double check because using these calculators on computers, they don't always register every button click. So 38,015 divided
Got
by,
the same. I got the same too.
you did? Okay, cool. Yeah, I got the same thing the second time. Cool. So what we have discovered is the specific heat of this new metal alloy that the engineers are considering using is about 497.4, which is actually pretty high for a metal. 900 is what aluminum is, so it's not as good as aluminum. But for instance, iron and steel is 450, so it's has a better insulating capacity than iron does. Way better than lead, way better than mercury or silver, but not nearly as good as wood or alcohol, which is not a metal, of course, or glass, which is not a metal either. Okay, any questions on that? All right, so that's another problem we've now worked, and they called it 500 flat, which they were thinking everything. Well, actually, they did say 497, but they said they ultimately rounded that to 500. So they got the same numbers we did, so that's good. So one thing you got to make sure is when you're doing these calorimetry, make sure you take into account all the different things. So just because it's a calorimeter in a calorimeter, that doesn't mean it's just the water and the thing you're sticking in the water. It has to include the inner cup too, but not the outer cup. So they could ask you a trick question like that. The outer cup of a calorimeter weighs blah, 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 and the inner cup weighs blah, blah, blah. And then ask this whole problem. And that giving you the answer, giving you the mass of the outer cup was just making sure you understand what the calorimetry experiment is. So make sure you don't fall for that one. Anybody have any questions on that kind of stuff? Now, if you're say a person that makes and sells food, like my friend from high school, Jimmy Miller, he owns a hot sauce shop in Virginia Beach called Speedy's Hot Sauce, and he makes Speedy's 44, Speedy's 43, Speedy's 47, all these different hot sauces. They're really good, by the way. But he makes them, and he makes them in his shop because his shop has a commercial grade kitchen in it. So when he actually made that hot sauce, the Speedy 44 was his first one. I think it was Speedy 44. When he made that, he then sent it off to Virginia Tech, and Virginia Tech put that food in a calorimeter, specifically a bomb calorimeter. And you basically just burn the food and see how much energy comes out of it. And then Virginia Tech will send you a detailed report telling you exactly how much it was. And that's what you have to have for a product that's like food related for you to actually sell it. It actually has to have calories and ingredients and all that good stuff. So a bomb calorimeter is what they use for that. So that's a neat little thing to read about if you want. After the bomb calorimeter, we're going into latent heat. This is what I was talking about before. I think the best diagram in the whole book is this one because it sort of helps you understand exactly what's going on here. So I'm going to more or less recreate the diagram because it helps me remember my numbers and all sorts of good stuff like that. So here's my axes. My horizontal axis is actually heat in kilocalories, which, remember, I told you earlier, the calories we have in food are supposed to be capital C, lowercase a, lowercase l. That's the same thing as a kilocalorie. The vertical scale, however, is temperature. So I'm going to write up here, and I'll write temperature, and that's going to be in degrees Celsius. And what we're going to start off with is basically water, ice. Whoa, Nelly. Okay, so we can start off by saying, let's demarcate this number down here as negative 40 degrees Celsius. And then I'll go negative 20, negative 10, 0. Now I'm going to go, I'm actually going to change the measurements up a little bit. 10, 20, 30, 40, 50, 60. Yeah, I definitely need to. So I'm going to, well, actually, I guess what I can do is I'll draw a break in the axis like this. Just draw a little break there. And now I'm going to put a line like that. That just means we're skipping a bunch of temperatures. So if I started here with, say, 60 on the line right above the break, 60, 70, 80, 90, 100, that doesn't go enough. So I'm going to start with 80. Whoa. So this mark right here is 80 degrees Celsius, 90 degrees Celsius, 100, 110, and 120. Okay. Now I'm starting with water, and water is going to be where I have added nothing. So the water is actually going to be frozen. And what's going to happen is the frozen water is going to take 20 calories. And by the way, this is 1 kilogram of water. And it's actually going to take 20 calories, which I'll indicate by this number right here. That's 20 kilocalories for it to reach from from negative 40 to 0. So that's the actual ice part. And then what happens is you put in 20 calories, you can calculate, because if you look at that table, the specific heat of ice is 0.5, if I remember correctly. So that's 0.5 calories per gram degree Celsius, if I remember correctly. Actually, let me look at that real quick. I'm looking back at that table again just to remind myself what water is and to remind you guys what water is. So water ice has a specific heat of water ice. Yeah, it's 0.5 calories per gram Celsius degree, which is essentially 2,100 joules per kilogram. So 2,100 joules per kilogram per Celsius degree is the specific heat of water. Since that's 2,100, if you actually put in 2,100 calories, that's the same thing as 2.1 kilocalories. And that's for 1 kilogram to go 1 Celsius degree. We went up 40. Yeah, so that's where we get that from. Now what happens is you've now actually got the ice up to 0 degrees Celsius. And what happens to water when it gets hotter than 0 degrees Celsius? When it's coming from lower than 0 degrees,
it starts getting colder.
Yeah, it'll actually it'll turn from ice to an actual liquid.
It'll start getting colder before it starts getting warmer. Is that what you're talking about? Or?
Oh yeah, it actually doesn't get colder, but the neat thing is it does in fact stay the same temperature until the entire liquid changes state. So what's going on is there's some vapor over it, so let's ignore that. But basically what's going on is every molecule of liquid is slowly of water is turning and breaking loose from the lattice that it made in its crystal form. And as that breaks away, it'll still stay 0 degrees Celsius until all of it has no lattice left. So what's going to happen now is that's going to go from 20 to 40 to 50 to 60 to 70 to 100 right here. Say 40, 60, 70, 80, 90, 100. So that's at 100 kilocalories is where the water finally melts. So what that means is it took an extra 100 kilocalories. Oh, actually, it took an extra 80 kilocalories because we were already up at 20. It took an extra 80 kilocalories to break the lattice. That's called the latent heat. Now what's going to happen is that 100, once 100 kilocalories have been put in, then I'm going to draw another gap in our axis. So I'm going to write like that. Actually, I wanted that in blue, not red. So here's another break. And Here's another break. And I'll do like that. Okay. So I'm now going to go by increments of say 50, and that would, I need to get all the way up to 7. So this would be, I could call this, for instance, 300 maybe. Let's try 300 and see what that works out to be. So this would be 300. This would be 400. Whoa, Nelly. A lot of bad stuff happened just then. So I'll say this one right here is 400, and then 450, 500, and then 550, 600, and then 650, 700. And then basically we're going to get up to about 740, which should be right about here. Okay. So what's going to happen now is, now that everything has changed states from the solid state to the liquid, the heat added will go to just heating up the molecules. In other words, making the molecules move faster. So they're all of a sudden going to jump up from 0 degrees Celsius to, crap, I actually added an extra thing here. So let's do this. The numbers didn't work out the way I had. I need the 200, because that's how many calories. The extra 100 is what it's going to take to move the water temperature from 0 degrees Celsius to 100 degrees Celsius. So I need that 200 in there. So what I'm going to do is I'll write right here and say this is 200 and 300, 400, 500, 600, 700, and now this right here will be 740. Okay, so that makes a little bit more sense. Now, the reason why I had to do that is I really need to show how much energy is going into heating the water up to get it up to 100 degrees Celsius. So that's going to happen from here to here. Okay, that's the not changing state. That's just changing the temperature. And at that point, all the temperatures now at 100 degrees Celsius. You can see that right there, just like this one was at 0 degrees Celsius. So the same thing happens again. All the molecules that are there are in a liquid state. And as you start to heat the raise the temperature to 100, or once you get the temperature to 100, every bit of heat you add in is sort of breaking the molecular bonds between adjacent molecules of water. And that takes a certain amount of latent heat before it can actually change state and completely break all the bonds between the molecules. And therefore, that's going to go all the way up to here, which I said was 740. So it isn't until we do that we can start then raising the temperature again, because now all the water has turned into steam once you've put in a total of 740 calories. And at that point, the water will leave rather quickly the gaseous state, or the liquid state, and become in the gaseous state. So I'm going to put it up like that. So what we have here, and this is the whole reason I like this diagram, is this diagram shows, in fact, that this right here, I didn't like that because it didn't make a straight line. So let's make a straight line. So that heat right there, notice it goes from 20 to 100. So that's 800, or excuse me, that's 80 kilocalories. And that's called the latent heat of fusion. Now, fusion means bringing the molecules together. So really, the 80 kilocalories is what is taken away from the solid chunk of, from the liquid water to make it into a solid chunk of ice. You not only have to lower the temperature to make it into a solid chunk of ice, you also have to extract some energy from it. And that's what that is. Now, when we get over here, we see at 200, this starts, whoa, hate it when it does that. At 200, this starts and it runs all the way up to 740. So 740 minus 200 is 540 kilocalories. And that's called the latent heat of vaporization. And that one is going the right way. That's you turning water into a vapor, i.e. steam. Okay. So this picture sort of shows exactly what the process is. MC delta T is the formula that's working on all the slopes. So this part right here is Q equals MC delta T, where T, by the way, or C, by the way, is specifically, we start off with ice, then we got it all to liquid water. So in this case, it's 1.00 calories per gram Celsius degree. Of course, I'm just giving it to you in the common number, not necessarily the graph that's shown. This part right here is Q equals MC delta T as well. But for ice, the specific heat is 0.50 calories per gram Celsius degree. And what's going on in this other part is, let's write it in, I'm going to write it in black, and that's Q is equal to M times LF. And this one is Q is equal to M times LV. Okay. Again, we have up here Q is equal to MC delta T. But now when we're in the steam state, it's a little misleading to talk about the steam state this way, but basically you can say the specific heat is about 0.48 calories per gram Celsius degree when it's in the steam state. Okay. So that's the extra part that we needed to understand to do calorimetry in general. So for instance, let's work a problem to help you with that. By the way, the book has a lot of tables of latent heats. It's got latent heat of fusion in kilojoules per kilogram. It also has it in kilocalories per kilogram, which is the same thing as calories per gram. And if I look at water, it says, in fact, it's 79.7. So it's not exactly 80. I'll say, whoa, I'll just erase that because I'm going to do something stupid. No, I'll make it approximately because it's actually 79.7 is the heat of fusion, and that's in calories per kilogram. Actually, calories per gram, not kilogram. Okay. And when I look at the heat of vaporization, I see that's actually 539. So I'll put again approximately here and say it's actually 539 calories per gram. Anybody have any questions on that? So let me show you an example. How much energy does it take? How much energy does it take to remove 1.5 kilograms of water at 20 degrees Celsius to make it ice at negative 12 degrees Celsius? So how much energy does a freezer have to remove? So here's our question. How much energy does a freezer remove? And now I'm making these numbers up. I'm not using the example from the book. How much energy does a freezer remove from, let's say, 3.00 kilograms of water at, let's say, 20.0 degrees Celsius. So you're imagining filling up, say, ice trays, a lot of ice trays, because it's going to take 3 kilograms, which is literally 3 liters of water. So I'm going to take 3 liters of water. I'm going to pour them in ice trays, and the water coming out of the faucet was already at 20 degrees Celsius. So that's what we're going to say. And we're going to turn it into ice at, and now let's say negative 10.0 degrees Celsius. So that's what we're trying to do here. We've got all our masses. So basically the air conditioner or the freezing unit is actually in charge of doing Q, and what we're asked for is the total Q. So I'm going to say solution. And what I'm using is Q is equal to MC delta T, and I'm using Q is equal to ML for the appropriate heats of fusion. So in this case, I'll say Q total has got to equal, and actually notice you're extracting heat, you're pulling heat away. So that's actually a negative amount of heat put to the water, because heat Q means heat added. So you can sort of think of it as heat being added to the refrigerator. I'm just going to compute the positive quantity because that's what I care about. So what I have is 3.00 kilograms of water. And that kilograms of water actually has a specific heat of 4,186 kilojoules per kilogram Celsius degree. And that water is going to go from a temperature of 20 degrees Celsius to a final temperature of 0 degrees Celsius. I want it to come out positive, so I'm going to say 20.0 degrees Celsius minus 0.0 degrees Celsius. That's the heat that has to be taken from the water just to get it to that freezing point. Now I've also got to actually convert it to a solid state. So that's a heat of fusion situation here. So that's 3.00 kilograms of water times the heat of fusion of ice. And that, if you look it up, is 3.33 times 10 to the 5th joules per kilogram. Actually, I think the other one was, yeah, that was joules per kilogram, not kilojoules per kilogram. Sorry about that. So 4,186 joules per kilogram. And I have the heat of fusion. So this is just the melting process. Now that I've got the water down to 0 degrees Celsius, and I've turned it into the solid state, I now got to take ice, which has a different specific heat, and change its temperature from 0 to negative 10. So now I'm going to say 3.00 kilograms times the specific heat of water, of ice is 2100 joules per kilogram Celsius degree. And in fact, that's going to go from, again, I want positive. So I'm going to say 0.0 degrees Celsius minus negative 10.0 degrees Celsius. So I can do all this 20. So I'm going to say clear 20. That's the change in temperature for the first part, 20 times 4,186 times 3. That's 251,160. And that's a buttload more sig figs than I actually have. So I'm just underlining the ones that aren't supposed to be sig figs. So that's just changing the water to temperature of 0 degrees. Now I'm going to take 3 kilograms and multiply that by 3.33 e to the 5th. And that gives me 999,000. Joules for the second term. That's just the dealing with the fact that it was in a free state, and you're now going to lock it into a lattice. And now I'm going to do the part where I'm making the ice colder. So in that case, I've got to multiply 3 times 10 times 2100. So 3 times 10 times 2100. And that gives me 63,000. And actually that first digit's not doubtful, but the last two are. So that's joules as well. So I'm going to say 63,000 plus 999,000 plus 251,160. That gives me a total amount of energy equal to 1,313,160 joules. I only had 3 sig figs, so all these underlines figures are not significant figures. And we can convert it to kilojoules to make it a little easier, in which case it's going to be 1.313 times 10 to the third kilojoules. Any questions about that? All right, well, that's about all the time we have. I actually ran about 4 minutes over. Hope you didn't mind. I know you guys got lab. We will finish up chapter 19 next time. Chapter 19 is a long chapter, so I don't feel bad about taking an extra day. I am pushing the homework assignment for 19 back. It's not going to be able to be due by this Sunday, obviously, or excuse me, by this coming Monday, obviously. So go ahead and have a good one. Thanks for coming, everybody. I'll wait for the last person to leave in case anybody has any questions. Oh, they left, all of them. They got the hell out of here.